Hi everyone, I'm Renata Sarmet's middle remains, and today I'm going to talk about a mimetic algorithm for the facility location problem. This work is supported by FAPESP and CNPq, and it was developed with Mário César Sanfelice, Pedro Rocama, Regina Berreta, and Pablo Moscato. First of all, let's briefly talk about what is the facility location problem, also called the UFL problem. So imagine there is a new city and you need to open some hospitals. But how many hospitals would you open and where would they be? In order to minimize the total cost. So the cost of building the hospitals and the cost of connecting patients to the hospitals. So for example, the distance between each patient and the nearest open hospital. The UFL is important in logistics and can be applied in several scenarios. In this figure, we can see that the blue circles are the customers and the squares are the facilities. So we chose a subset of facilities to open, the red squares. In this work, we implemented a late acceptance algorithm and also we designed a mimetic algorithm for the UFL problem. The mimetic uses both approximation algorithms and search heuristics to find initial solutions and to improve the solution during its generations. Due to time limit, in this presentation we are going to focus on the mimetic algorithm. Before I start talking about the mimetic algorithm itself, we must do an overview of the fundamental algorithms that we are going to use inside the mimetic. The first one is a 1.61 approximation algorithm proposed by Jain et al. That has a grid approach. The map grid, it's a random procedure which generates solutions for the following steps. First, we choose a subset of facilities using one of the two random approaches, sampled or shuffled. Then we connect each client to its closest facility in this subset and we remove from it any facility that wasn't used. Finally, an instance is built only with the facilities remaining in the subset and GR runs on this instance to produce our solution. The local search, our implementation of the 2.414 approximation algorithm. It starts with an initial solution and seeks to improve it. It maintains a non-empty set of open facilities and assignments of clients to those. It changes from one solution to another considering three types of move: open facility, closed facility, and swept facilities. We repeatedly check if any of these changes to the current solutions reduce the total cost. If so, we make the move and update the current solution. Once no further changes decrease the total cost, we stop. This solution is said to be a locally optimal solution. The tabu search and the late acceptance, both are meta risks derived from local search, but unlike local search, they both accept no improving moves in order to escape from local minima. They also consider just the simple moves, open or close a facility. The tabu search is a simplification of the one proposed by Sun, in which we use just the short-term memory. In the late acceptance, our accepting criteria is that if the solution is better than the current one, or if it's better than the solution considered a number of iterations before. If we achieve the maximum number of iterations in which the current solution does not improve, or number of iterations without improving the best solution found so far, we stop. Now let's dive into our mimetic algorithm, also called MA. Similar to the genetic algorithm, the mimetic is a population-based meta risk. It is an evolutionary algorithm that consists of an initial population composed of chromosomes, also called individuals, each one representing a viable solution to the problem. At each iteration, the algorithm generates new individuals using crossover and mutation operators. Unlike the genetic algorithm, the mimetic uses extra knowledge, such as heuristics or exact methods, to improve the solutions in the populations. Also, our mimetic algorithms use a structured population. An individual corresponds to an array of booleans with size equals to the number of facilities, representing whether the facility is open or not. Our population structure. We have a three-layer ternary tree. At each node we have two individuals representing one pocket and one current. Also, we call the node 0 as the root of the tree. There is a pre-established order in the tree structure that we must always respect. In every node, the pocket solution never costs more than the current one, and also the pocket of the parent never has a solution cost greater than the pocket of its offspring. Each time an operation that modifies the individuals is performed, we must update the population from bottom to top. And also, to find even better solutions, when the pocket in node 0 is updated, we run the tabu search. Population initialization. The pocket and the current of every node must be initialized with an initial solution. Here is where we combine our mimetic algorithm with approximation algorithms. So, the pocket of node 1 is initialized with a solution generated by the grid approximation algorithm. The pocket of node 0, the root, is initialized by applying the local search to the pocket of node 1. And every other pocket and current are initialized using a random procedure map grid. After the generation of the initial population, we must update the population, establishing the order where the best solutions are above in the tree. Crossover and mutation. Crossover is the operation that generates a new individual, called offspring, through the exchange of genes between two individuals, called parents. Mutation is the operation that changes the status of a facility in order to restore lost or unexploited genetic material. So it's changed the status between open and closed. 4 different crossovers were implemented and tested: the uniform crossover, the one-point crossover, the groups crossover, and the union crossover. The first 2 are quite common in the literature, and the last 2 were created in an attempt to build a crossover with a more specific knowledge of the problem. So, the uniform crossover copies for the offspring what is the same in both parents and draws what is different, with a 50% chance of opening or not the facility. The one-point crossover draws uniformly at random a number n from 0 to the number of facilities, and then copies information from one parent on the first n facilities and the rest from the other parent. The groups crossover identifies clients which are connected to a common facility in both parents and define them as a group. If a group was connected to the same facility in both parents, this facility is open in the offspring. Otherwise, we find the facility which minimizes the cost of connecting that group to and open it in the offspring. And the union crossover copies all open facilities of each parent to the offspring, keeping the others closed. To create the next generation, we consider a subpopulation with a parent and 3 descendants. So, from top to bottom, we combine the pockets and currents in this specific order through the produce procedure. So, how is this produce procedure? First, we apply the crossover to a pair of pocket and current, generating the offspring. Then, we apply the mutation to this offspring, and finally, we apply a heuristic to improve the resulting individual. After that, the population must be updated. In order to decide which heuristics to use to improve each individual, 2 strategies were established. The first is deterministic and the second is probabilistic. More likely to use cheaper methods, but some likelihood of using table search. So, the overall of the mimetic algorithm is: we must initialize the population, then we produce new generations, and from time to time we change the root, and we must always keep the population updated. The algorithm ends when this root exchange process achieves the stopping criteria. Now let's talk about the computational results, once again focusing on the mimetic algorithm. We use 90 instances of Cork-Algorithms symmetric and asymmetric packages. These instances have the same number of customers and facilities, ranging from 250, 500, and 750. All experiments were performed in the same computer with the technical details described, and all the codes were implemented in C++. For each algorithm, we compare the cost of the solution found with the best upper bound. We performed several tests with the tree structure, the crossover we use, the way we generate the initial population, the produce strategy, and all the other input parameters. After all, the best configuration we found is using the uniform crossover with shuffled initial population and the probabilistic produce strategy. For most instances, it has obtained solutions with gap really close to 0% compared to the best upper bound, with only a few instances slightly larger than that. Analyzing the time, instances of size 250 took around 17 seconds, those of size 500 took around 130 seconds, and those of size 750 took around 440 seconds, maintaining this pattern even though alternating between the symmetrical and asymmetrical packets. Here's the overall results. As you can see, the mimetic algorithm was the one that found the best solutions, being very close to the best upper bound, but it also spent much more time than the others. So, in this work, we implemented a late acceptance algorithm for the UFL problem based on the framework of Burke and Baikov. Also, we designed a mimetic algorithm for the UFL inspired by Harris et al. In particular, this later algorithm uses approximation algorithms, search heuristics, and randomized procedures to find initial solutions and improve the solution during its generations. Our proposed mimetic algorithm found excellent solutions with costs very close to the best upper bound. However, depending on the size of the instance, it also had an expensive computational cost. On the other hand, search heuristics such as delayed acceptance achieved good results in a more reasonable time, although it could not match the table search results. This research was supported by FAPESP, first with a scientific initiation at UFSCar and then with a research internship at the University of Newcastle in Australia. Thanks for watching, I hope you want to read the full paper.